a magnitude 9 earthquake could strike the west coast. And scientists just updated their odds of exactly that happening using a method they have never applied to this specific fault before. Off the coast of the Pacific Northwest sits a fault line capable of producing one of the most destructive earthquakes in American history. And researchers are watching it more closely right now than at almost any point in recent memory. So let's get right into exactly what this fault is, what the new research says, and what scientists are watching for next. Let's start with the fault itself, because understanding its basic structure explains everything else about why this specific hazard concerns scientists so much. The Cascadia Subduction Zone stretches roughly 600 to 700 miles along the Pacific coast, running from Northern California up through Oregon and Washington and into British Columbia. At this boundary, the Juan de Fuca Plate, a smaller oceanic plate, is being forced underneath the much larger North American plate at a rate of approximately 4 centimeters per year. That might sound slow, but because the two plates are essentially stuck together rather than sliding smoothly past each other, that steady motion generates enormous, continuously building pressure rather than being released gradually. Eventually, the accumulated tension exceeds what the locked plates can tolerate, and when they finally slip free, an earthquake spreads along the entire boundary all at once. This exact kind of earthquake, called a megathrust earthquake, occurring at boundaries where one plate slides beneath another, is capable of producing some of the most powerful earthquakes on the entire planet, comparable in scale to the 2011 earthquake that struck Tohoku, Japan, the 2004 earthquake that struck Sumatra, and the 1960 earthquake that struck Chile, still the most powerful earthquake ever recorded anywhere on Earth. According to the Pacific Northwest Seismic Network, this activity makes the Cascadia Subduction Zone capable of producing earthquakes up to magnitude 9. Here is a detail that makes this fault genuinely unusual, and it is part of why scientists have had to work so hard to understand its true risk level. Unlike other subduction zones around the world that produce frequent, smaller rumblings as the plates scrape past each other, Cascadia stays remarkably quiet, showing very little ordinary seismic activity. For a long time, this quiet behavior fueled assumptions that the plates were simply locked together by friction, holding steady without much strain, an interpretation that turned out to be genuinely misleading. According to Maureen Denault, an associate professor of Earth and Space Science at the University of Washington, that quiet surface behavior actually masks something considerably more dangerous and happening underneath. Let's talk about what researchers actually found, because this is the newest and most significant piece of this entire story. According to research published earlier this year in the journal Science by scientists at the University of Washington, there are specific pathways within the fault itself, described as highways that transport migrating fluid through the rock. This moving fluid actively facilitates further weakening and stress buildup along the fault. Denault described the implications of this discovery directly, noting that while the finding remains preliminary, the team believes these variable fluid pathways in Cascadia will meaningfully change how large earthquakes actually behave once they begin, potentially affecting how a rupture spreads along the fault once it starts. This fluid pathway research connects to a fundamentally important question scientists have been trying to answer for years: whether Cascadia is more likely to rupture as one single enormous event stretching across its entire length, or whether it tends to break in smaller, more localized segments instead. According to the research team's stress testing analysis, the variability in these fluid pathways appears to directly influence how stress transfers along different sections of the fault, which in turn affects whether a rupture beginning in one location is more or less likely to propagate into neighboring sections rather than stopping short. Understanding this mechanism matters enormously for earthquake preparedness, since a full-length rupture spanning the entire 600-plus-mile fault would produce an entirely different and considerably more catastrophic scenario than a partial rupture confined to just one segment. Now let's get into the actual updated probability numbers, because this is where the newest research has made a genuinely significant change to how scientists describe this risk. An updated report from the United States Geological Survey indicates that the probability of a magnitude 9 earthquake occurring somewhere along the Cascadia Subduction Zone has risen to 15% within the next 50 years. What makes this specific update genuinely significant is the methodology behind it. This study incorporates, for the first time, the actual time elapsed since the region's last major seismic event directly into its mathematical modeling, using advanced techniques combined with paleoseismic records, physical evidence of ancient earthquakes preserved in coastal sediment layers and buried forests, stretching back thousands of years. According to that same USGS analysis, the Cascadia Subduction Zone exhibits genuinely cyclical behavior, having produced at least 19 major earthquakes over the past 10,000 years, occurring roughly every 500 years on average. Researchers have dated the fault's last major rupture precisely to the night of January 26, 1700, identified through a combination of Pacific Northwest geological evidence and, remarkably, detailed written records from Japan documenting an unexplained tsunami that struck its coastline that same night, arriving without any felt earthquake beforehand, since the actual rupture had occurred an ocean away. That means this fault has now gone more than 320 years without releasing its accumulated strain, a stretch of time that, while not automatically meaning a rupture is imminent, does place the fault well within the range, where its historical cycle suggests renewed activity becomes increasingly plausible. It is worth being precise about what this 15% figure actually represents, since even a full-length magnitude 9 rupture is only one possible outcome among several the USGS report considers. Even if a complete, full margin rupture does not occur, the report specifically warns about high-risk scenarios involving partial ruptures instead. Mathematical projections suggest that in the southern segment of the fault, specifically, the probability of a magnitude 8 or greater earthquake rises considerably higher, reaching 30% within the next 50 years. Separate analysis breaking down these scenarios in more detail estimates that a partial rupture, involving only the southern portion of the zone, would likely produce an earthquake somewhere between magnitude 8 and 8.6, carrying a 37 to 43% chance of occurring within the next 50 years. A full margin rupture, where the entire zone gives way simultaneously, would produce a considerably larger event somewhere between magnitude 8.7 and 9.2, with researchers placing that specific scenario's probability at 16 to 22% over that same 50-year window. Let's talk about what actually happens on the ground if and when this fault does rupture, because the scale of destruction involved here is genuinely difficult to picture using ordinary earthquake experience as a reference point. This 1,000-kilometer fault line poses a direct threat to major urban centers, including Seattle, Portland, and Vancouver, home to more than 10 million people combined. According to detailed seismic hazard modeling, a full magnitude 9 rupture would produce somewhere between 3 and 6 minutes of violent, continuous shaking, with some estimates from Oregon's own State Emergency Management Office placing that figure even higher, at 5 to 7 minutes of shaking along the immediate coastline, with intensity gradually decreasing the farther inland you travel from the coast. For comparison, most earthquakes people have direct experience would last only a matter of seconds, making a multi-minute rupture of this scale almost impossible to properly imagine without having lived through something comparable. According to FEMA's own modeling, a magnitude 9 earthquake striking the Cascadia Fault would kill an estimated 14,000 people across Oregon and Washington combined, with additional casualties expected in Northern California and British Columbia, depending on the exact rupture pattern. And the earthquake itself represents only the first phase of this disaster scenario. Following the shaking, a resulting tsunami reaching up to 100 feet in height along the immediate coastline would strike within minutes, far too quickly for any conventional evacuation to occur after the earthquake itself, meaning coastal residents would need to begin evacuating to higher ground immediately once the shaking starts, rather than waiting for any official tsunami warning to be issued. That tsunami would not remain confined to the Pacific Northwest either, with modeling showing the resulting wave capable of reaching across the Pacific Ocean toward Japan and Hawaii as well, based on the historical precedent set by the 1700 event's own documented tsunami reaching Japan's coastline. The disaster's aftermath carries its own severe, extended challenges beyond the initial earthquake and tsunami. Oregon's Department of Emergency Management has specifically warned that coastal populations would become isolated into effective islands following such an event, cut off by landslides, soil liquefaction, and damaged infrastructure, including collapsed bridges, a scenario the department has mapped in detail through what it calls its Cascadia Island Mapping Pilot Project. Given current regional preparedness levels, Oregon's own emergency planners anticipate coastal communities could be without basic services and outside assistance for at least 2 weeks following a major rupture, and possibly considerably longer depending on the specific severity and scope of infrastructure damage. Let's address directly what all of this means for anyone living across the affected region right now, since a 50-year probability window can feel simultaneously urgent and comfortably distant depending on how you look at it. Chris Voss, Emergency Management Director for Multnomah County, Oregon, has summarized the fundamental uncertainty here about as clearly as possible, noting that what scientists call the big one could happen in 5 minutes, or it could happen in hundreds of years. What remains certain, according to Voss, is simply that it will happen eventually, which is exactly why counties across the region continue working to mitigate its eventual destruction through ongoing intergovernmental and interagency collaboration, rather than treating the 50-year statistical window as any kind of reliable countdown clock. It is also worth understanding that this Cascadia risk does not exist in complete isolation from other major West Coast fault systems either. Separate research published this year has found evidence suggesting that a major Cascadia earthquake could potentially trigger a second connected earthquake on California's San Andreas Fault within a remarkably short window of time, based on unusual sediment layer patterns discovered through drilling conducted off the coast of Oregon. That research suggests the traditional picture of a single, isolated West Coast earthquake disaster may actually understate the true worst-case scenario, raising the possibility of a coast-wide sequence of major earthquakes striking multiple regions within hours of each other, rather than a single, catastrophic event confined to just the Pacific Northwest. So what should residents across this region actually do with this updated risk information right now? Washington State has already implemented tsunami warning systems, designated evacuation routes for coastal communities, and deployed the Shake Alert Earthquake Early warning system, which can provide anywhere from 10 to 90 seconds of advance warning before shaking from a distant Cascadia rupture actually arrives at your specific location. A genuinely valuable window for taking cover or triggering automated safety systems. Despite these preparedness measures, regional infrastructure, including bridges, ports, the electrical grid, and water systems, retain significant, well-documented vulnerabilities that continue to be assessed and addressed on an ongoing basis. If you live along the immediate coastline anywhere within this zone, know your tsunami evacuation route to higher ground and understand that following a major earthquake, you should begin evacuating immediately rather than waiting for any official warning, since the tsunami itself can arrive within minutes of the shaking stopping. If you live anywhere farther inland but still within the broader region, maintain a genuine multi-week emergency supply kit, given the realistic expectation of extended isolation and delayed outside assistance that regional emergency planners have already built into their own response modeling. It helps to understand a bit more about how scientists actually reconstructed a precise date for an earthquake that happened more than 3 centuries ago, since that detective work is genuinely remarkable in its own right. The physical evidence in the Pacific Northwest itself comes largely from what researchers call ghost forests, stands of dead cedar trees still standing along the coastline in places like Washington's Nescoan area, killed when the 1700 earthquake caused the coastal land they were growing on to suddenly drop several feet, allowing salt water to flood in and kill the trees where they stood. By analyzing tree rings from these preserved ghost forests, researchers were able to narrow down the year of that sudden land subsidence with real precision. The final piece, connecting that physical evidence to an exact date, came from an entirely different continent, detailed Japanese historical records documenting an orphan tsunami, a wave that struck the Japanese coastline without any preceding earthquake, felt locally, since the actual rupture had occurred entirely across the Pacific Ocean. Cross-referencing those Japanese records against the tree ring evidence allowed researchers to pin down the Cascadia rupture to the specific night of January 26, 1700, an extraordinary example of how physical evidence from opposite sides of an entire ocean can be combined to reconstruct a single historical event with genuine scientific precision. It is also worth understanding why this fault's habit of rupturing roughly every 500 years, based on evidence of 19 major earthquakes across the past 10,000 years, does not translate into a simple, predictable countdown the way that average might initially suggest. Earthquake recurrence intervals along faults like Cascadia are not perfectly regular the way a clock ticking at a fixed rate would be. Some gaps between major Cascadia ruptures in the paleoseismic record have been considerably shorter than 500 years, while others have stretched out considerably longer, reflecting the genuinely complex, only partially understood physics governing exactly how and when accumulated stress along a fault this large finally releases. This is precisely why USGS researchers describe their updated 15% 50-year probability as a statistical likelihood grounded in the fault's broader historical pattern rather than a specific prediction pointing toward any particular year or even decade when the next rupture will actually occur. There is also a meaningful distinction worth understanding between how earthquake risk gets communicated for a fault like Cascadia compared with more frequently rupturing fault systems elsewhere. Because Cascadia produces such enormous, infrequent events separated by centuries of relative quiet, scientists have far fewer historical examples to work from, compared with faults that rupture more regularly on human observable timescales. That relative scarcity of direct historical data is exactly why new research techniques like the fluid pathway analysis published this year carry such significant weight when they emerge, since each new methodological advance represents a genuinely rare opportunity to improve scientific understanding of a fault system that simply does not offer researchers the luxury of studying frequent, smaller-scale ruptures the way many other active fault zones around the world do. Let's bring this all together. The Cascadia Subduction Zone, a massive fault line stretching along the Pacific Northwest coast where the Juan de Fuca Plate is slowly being forced beneath the North American plate, is capable of producing a magnitude 9 earthquake, And an updated United States Geological Survey report has raised the probability of exactly that scenario to 15% within the next 50 years, using modeling that incorporates the time elapsed since the fault's last major rupture back in 1700 for the first time. New research from the University of Washington has identified specific fluid pathways within the fault itself that appear to actively weaken it and could meaningfully influence how a future rupture actually spreads once it begins, adding genuine new understanding to a fault that has long puzzled scientists with its unusually quiet surface behavior between major events. Whether the eventual rupture takes the form of a partial break confined to the fault's southern segment, carrying roughly a 30% chance of a magnitude 8 or greater event, or a full-length rupture reaching magnitude 9 or beyond, the resulting disaster would bring several minutes of violent shaking, a tsunami reaching up to 100 feet along the coast, and weeks of isolation for coastal communities cut off by damaged infrastructure, according to FEMA and regional emergency management modeling. Scientists cannot tell us exactly when this will happen, but the growing body of research into this fault's internal structure and historical behavior continues sharpening our understanding of exactly what to expect once it finally does. I will keep tracking this research closely, especially any further findings on how those newly discovered fluid pathways influence rupture behavior. So make sure you are subscribed to the channel and have notifications turned on for whenever there is meaningful new research on this fault. Thank you all so much for watching today's video. This single fault line off the Pacific Northwest coast represents one of the most significant natural hazards anywhere in the United States. And scientists are working harder than ever to understand exactly what it has in store. I will see you in the next one.